All right, so the biweekly yesterday morning, uh, it was like not the hardest one. Like the top person finished in like 10 minutes. And I broke my record on this one. This is my best yet. So hopefully it gets me to Guardian, but we'll see. So maximum sum with exactly k elements. What do? You take a number from the nums, uh, and then you add m plus 1 to it, and you increase your score by m. And the thing to kind of deduce is that you'd always want to take the maximum thing. So you'd be like, take 5, add 5 to our score, make 5 6. Take 6, add 6 to our score, make 6 7. Take 7, add 7 to our score, make 7 8. And you pretty much only ever want to do that. So you're just returning what's the maximum of nums. You're going to take it k times, and then you're going to have everything you've added to it as well, which is k times k minus 1 over 2. Because first you're adding 1, and then you're adding 2, and then you're adding 3, and so on, and up to adding k minus 1. And this is just what that looks like. This is one of these things you just kind of learn with, like, what's the sum of everything from 1 up to a given number. It's k times k minus 1 over 2. So that one's like actually pretty interesting for a first problem, just in that you kind of can deduce a little bit. Find the prefix common array of two arrays. This could have been a really interesting problem. What should have happened is that this could have been Q3, and they could have made the constraints a lot tighter, and then Q3 could have been Q2. Because you start and it says return the prefix common array of A and B, the prefix common array being the count of numbers that are present at or before index I in both A and B. So it starts out in the prefix common array as 0 because A has just a 1 and B has just a 3. And then it jumps up to 2 because A has a 1 and a 3, and now B has a 1 and a 3, or a 3 and a 1. And then 3 because 1 3 2, 1 3 2, and then 4. Yeah, I immediately started thinking, well, what are interesting ways you could do this in linear time? If this was n could go up to 10 to the 5th, then it would be really interesting, but it doesn't. So you can just do it in O of n squared, which just looks like adding both running prefix arrays of each into a set, and then just taking the intersection of both of those sets, and that's like the length of that is the number of elements that's going to be at C at I. If you didn't do this, I think you could still use like a set and a pointer or something. It would be a little more interesting, but the takeaway with these problems, if I'm thinking about the takeaway for each of these, for me, the takeaway of this one is like, look at the constraints. Sometimes it allows you to get away with something easier. And even if, like, I literally did the mental math in my head while I was doing this, like, I felt like I almost had a solution that would have been in linear time. And it was like even a little longer than this. And it didn't take me that long to type it out, but there was some like slight refining that would have taken a little bit of thought. And I was just like, no, I could literally just trash this and do an intersection of two sets every step of the way because I can get away with it. And even if it's like I have to start over and type more code, it's just way faster to type that because it's so much simpler. And with this one, the lesson's probably like be pretty confident, like run the example test cases and be like, looks good. There's not really any corner cases I can think of that would really mess this up all that bad. And trust yourself is the lesson to be learned on that one. I'll keep these open just in case. All right, max number of fish in a grid. You can also see, this is a little metagame thing, like 6,000 people did this. So this was like trivially easy compared to a normal Q3. These ones, I don't normally have the impulse to look at how many people accepted at any point. But yeah, like above 10,000 is kind of reasonable for these. For this, probably like 2,000 is maybe average. And then for the Q4, around like 700 is maybe average. So this was significantly harder than your average Q4 for most people. And this was significantly easier than your average Q3. So for people on YouTube, you can just pause. But pretty much we're taking a flood fill. We're saying we have these little islands of water. It's swapped from normally how it's phrased. But we have all these numbers, and we want to see like what's the maximum like contiguous sum of numbers pretty much that forms a 4-directional island. So here it would probably be 7 because we have this 3 and this 4 next to each other, and it's separated by these zeros from everything else. And I mean, it's a pretty basic like grid traversal. So I just say like for I in range M, for J in range N, continue if it's 0, because that means that we're on land, because the canon is that there's this fisher person that's trying to get the most fish. And make a stack and just do a depth first search, and every step of the way. I mean, the slight little twist here that makes this different from like largest islands or something is that the islands are weighted, where each square can have a number, and you're taking a sum of all the squares rather than like a count of all the squares. But that's very, very simple. That's just cur plus equals grid at x at y instead of cur plus equals 1. And then you can keep a scene set, or you can just set everything you've seen to be 0 and continue, and then take the max so far. So that one was, for me, this came down to how fast can I possibly do this and not fuck it up, which actually is, I guess that's where like the competitive coding comes into this in a different way, is like, how fast can I type this up? Like, for example, I've typed this exact line maybe 100 times now, and I'm very quick. And I don't know why. I always start with, actually, I do know why. -1, 0, 0, 1. It's because this is clockwise. Like, this would be 12 o'clock. This would be 3 o'clock. This would be 6 o'clock. And this would be 9 o'clock. Just an interesting little note about my code. But it is important to write this the same way. If every single time I was like, okay, we got 1, 0, we got 0, 1, and then we need this one, and then what's the last one that I need? Oh, 0, -1. That kind of thing is what slows down your typing. That kind of thing, and also getting used to, like, at least on a Mac, like command arrow allows you to go to like the beginning of a line versus the end of a line. Or option arrow is like go over one word at a time, which is surprisingly actually used more than I find anything else personally. But that's the kind of thing, if it's like this scenario where you're just like, okay, I know what has to happen. I have to do this flood fill and find the largest islands that are weighted. Okay, there's one line that's going to be different from the other dozen times that I've typed out this exact code. Then you do get into the nuances of like, how fast can I type? This one, not so much though. So this one, it says you have an array. You can do one of two things. You can either remove the first value if it's the smallest value, or you can move that value to the end of the array. So here you'd want to move the 3 to the end, and then you'd have 4, -1, 3, and then move the 4 to the end, then you have -1, 3, 4. Then you can get rid of the 1, or the -1, and now the 3 is the smallest, so you can get rid of that, and now you have a 4, and you can get rid of that because it's the smallest thing of just itself, and then you have nothing. So it takes 5 steps total. If you have 1, 2, 4, 3, you remove the 1, remove the 2, got to move the 4 to the back, and then remove the 3, remove the 4. So it also takes 5. For 1, 2, 3, it takes 3 because you're just deleting each element. It's already in ascending order. All the values are distinct. It's 10 to the 5th, so you got to do it in linear time or n log n. So my first thing I noticed was, okay, well, the first thing that we can do, this first step of, or the second thing, I guess, of putting an element from the front to the back, that's the same as rotating the array. So every single time we have to rotate the array until we get the smallest element. That's the only thing we can ever do. So we got to rotate the array, which means that really what we're looking for is the difference between indices of the smallest and the next smallest element. So here, like -1 is at index 2. 1 second, my dog wants to go outside. You can go. Yeah, she wants to go lay on the bed. Here, -1 is at index 2, so you got to rotate 2. You got to get rid of this 3 and rid of this 4. You got to do something with them. And then you're at -1. And then also the 3 is right after the -1 if we think of this array as circular. If we think of it as like wrapping around, and 4.next is -1, -1.next is 3. So my thought was then, okay, what if we sorted the array so that we're looking at the smallest and then the second smallest, but then we retain their original indices. So we're like, this is at index 2, this is at index 0, this is at index 1. And then we can say, how many steps does it take to get from one element to like pivot to another element, well, it's going to be the difference of their indices. So to pivot from our starting index of index 0 to index 2 is going to take us 2 pivots to get to this -1. And then if we think of it as circular, it's the other case is if we want to pivot from an index to an earlier index, aka we want to wrap around, that's kind of just like n minus this index to get to wrap around plus this new index, which I have right here. But I mean, we'll get to exactly what that means, but and that's where I started. That's where I said, all right, that makes sense to me. So I sort it and I keep track of the original indices. And then I say, okay, look at every index. We immediately just don't even care about the actual value anymore. That can just be whatever, because we used that information to sort the array. But now that we've sorted it, we no longer care about that value ever. That's like a non-factor in the question at this point. We're never going to change the order or anything. It's already sorted to be what it's going to be. So the fact that this is -1 versus -10 doesn't matter. All that matters is that it's like less than this and less than this. Anyway, and then we have a little bit, I mean, it's pretty much like I keep track of the index of the previous number, the previous minimum, and the index of the current minimum. And I pretty much do that math. I say, like, what's the index of the current minus the previous? Well, if the previous starts out at 0, say, and then we're going to -1, the index of the current is 2. And previous, because we're starting out at index 0, right? That means we got to rotate twice before we can get to this -1. And then every step of this for loop, I'm also saying like res plus equals 1. Like we got to actually specify, all right, delete the element. And then there's a couple of other things. So the first thing that I realized, because obviously this code is more complicated than what I was just saying. The first part is, okay, well, what if we have to wrap around the end? Well, that's not going to be the current index minus the previous. That's going to be the current index plus n minus the previous. The second thing is that the size of the array is changing. Like, none of these examples actually do it justice, which I think is part of what makes this problem as confusing as it is potentially for people. But if you take, for example, this one, you delete 1, you delete 2, you got to move 4 to the back, and then you delete 3. But then there was only 3 and 4 at that point. You'd already deleted index nodes 1 and 2, or elements 1 and 2. So when you move this 4 to the back, it's not like you're saying, well, the length of nums is 4, and then you delete 3, and then 4, you have to wrap all the way back around to get to 4. That's not the case. You delete 3, and you have to wrap all the way back around 1 element to get to 4. In fact, no elements, because at that point, you've deleted the 3. The only thing left in the array is the 4. So that's why at first I was like, all right, you got to actually dynamically change the size of the array itself to account for the fact that in this situation, 4, 3, and then 3, 4, and then you delete the 3, and then the 4 is just right there. There's not a 1 and a 2 in the way. That's good. But then there's actually another situation that's accounted for, and it's if you had like, let's see, if your array was something like, and I literally typed this out, 6 in the contest, 4, 2, 1, 3, 5. Oops, something like this. So here we want to start at the 1. And then we want to go to the 2, and then we want to go to the 3, and then go to the 4. And then we'll find ourselves in a situation where right here, if we want to go to this 5, we don't have to skip over 3 elements. These elements are gone. So really what we want is to be looking at an array that's ostensibly this, 6, 4, 5, and then say we're going from index 1 to index 2. And this notion that we're going from index 1 to index 2, 3, 4, 5 is nonsense. It doesn't matter because we've deleted some amount of elements. And it could have easily been 6, 4, 2, 10, 3, 5. And then there's no predictable way to know, well, okay, now it's index 1 to index 3. There's no way to know without specifically dealing with the indices of each of these. And then you got to think, all right, well, That's not a good sign. We want to maintain a list and delete indices from the middle. That's an O of n operation for every time we delete an index. And we deleting every index, so that's O of n squared, which is not going to pass. But then you can think, aha, wait a minute, sorted list, that's what I want. Because a sorted list, pretty much every operation is O of log n, or a multiset in other languages. So that's why all of these, I'm not saying like, initially I just had like res plus equals idx minus prev. This would be like res plus equals just 5 minus, like the index of this 5 minus the index of this 4. Because, okay, you're at the 4, and then you got to pivot, and then say put all these at the end or whatever you're going to do. But that doesn't make sense because you're pivoting through a lot of like ghost elements that you've supposedly deleted. So that's why instead of idx minus prev or idx plus n minus prev, it's actually sl.index minus prev. And then I set prev to be sl.index of the last thing. And then SL is a sorted list that I'm actually maintaining. So SL, I say, okay, it starts out and it just has every index 0 through the length of nums. And it's like, great. And then at some point we're going to say, hey, how much does it cost me to get from index 1 to index 5? And we'll have manipulated the SL over time to be, well, we got rid of a 3 and we got rid of a 2. And now we're looking at our sorted list is 6, 4, 10, 5. So index 1 or element 1 to element 5 in the sorted list, representing indices of the original array, the index that they are in the sorted list is index 1 and index 3. And then we can say, well, we got to rotate twice to get there. And that's exactly what this does. So I say, okay, SL is a sorted list, and it's just range length nums, because this represents not necessarily the elements, but all the indices from 0 to the length of nums. Because we just want to see, again, like, what's the distance from index 0 to, say, index 10 if we deleted some amount of indices in the middle. And that's exactly what we do. So we say, what's the difference between the index of IDX and whatever the previous index of the previous IDX was? And then in the end, not only do we say res plus equals 1 to actually spend the step to delete the element, but then we just say sl.remove IDX. And you could have used a segment tree. I started typing out a whole segment tree thing, but this is so much simpler and easier in Python. It's like a built-in data type to the standard library, so I'm always kind of looking to use that instead. And it has yet to be disproven that you can always use a multi-set over a segment tree. I have not found a scenario where you need a segment tree yet. And it's n log n time, right? Because every operation is just log n to change the sorted list. And that easily passes. Yeah, so that's this contest. I'm finding that personally I thrive in these easier contests where, I mean, this problem was actually not easy. This was a pretty difficult problem, but the other problems were like pretty approachable. And I tend to thrive with that, maybe because I type quickly or something. This error was before I had used a sorted list. I thought I sort of did this false deduction in my head where I was like, if we go back to, if this was like 6, 4, 2, 3, 10, 5, something like that. In my head, I was like, I think I had this failure of visualization where the way I was visualizing it was a little bit inconsistent, because a lot of what we're doing that's actually the hard work here is, okay, yeah, we're like changing things in SL, sure, but we're not like necessarily deleting elements from the array. We've like sorted the array and then we're just parsing through it with a for loop. And then we're just saying we have this index that we're currently at and we have the previous index that we were at. And where I kind of had this failure of imagination is where I went, well, we've accounted for this varying length with n minus equals 1 every time we delete an index. That's cool. So if we have, say, like, we've deleted 2, we've deleted 3, we need to get to 5, how far does it take us to get there? I was thinking something along the lines of like, well, because we've rotated the array, that will have been accounted for, the distance to get from 4 to 5. But then that was actually why I typed out this exact example. This exact example, this 642135, because here it's easy to visualize when you have this sort of concave, like descending, descending, ascending, ascending. Once you delete these, there's no wrapping around the end of the array to get from these high numbers in the beginning to this high number at the end. So it's not actually always accounted for when you say n minus equals 1. You also need to account for exactly which specific indices have been removed. You wouldn't have to if you were actually rotating the array, if I'm not mistaken. And I think that's where I messed up, because I was imagining, well, we're rotating the array, but it's like, we're rotating the array in theory. Really, though, I've already cut the corner of just using a for loop on a sorted array. So actually, I'm totally not rotating the array. That's just sort of a representation. But this has, if I were to say 6 goes from here to the end, like, I'm not cutting the corner that I'm cutting in this code. So that would be O of n squared, and I think that's where a lot of people got TLEs and couldn't get it. But the trade-off is that if I'm not actually doing that and I'm sorting this and retaining original indices, then I have no way of using the length of the list to know the distance between my current min and the next min. And that's why you do need to make that trade-off of having some sort of data structure that maintains exactly which indices have been removed. And I didn't really realize that at first, which was my mistake, but still a pretty fun problem. Yeah, that was this contest.